Hi everyone, I'm Aaron, this is Nikita, and that's Rohan, and we are from machine learning at Berkeley. So today we are going to talk about TensorFlow. It's part of our workshop series. So let's begin with what is TensorFlow. So before TensorFlow, we need to understand what's a tensor. So a tensor is an n-dimensional array of numbers, and so one dimension will be a vector, 2 dimension is matrix, 3 dimension and above is, we call it a tensor. So TensorFlow is just tensor plus flow. So what do we mean by flow? So TensorFlow is an open source library for numerical computation, and when we say flow, we mean data flow graphs. Because we need TensorFlow has this feature that separates definition of computations from their executions. So we define computations in the form of graphs, and there are two phases. One is to assemble a graph, and then the second one is to execute it in a session. So why do we use TensorFlow? It has a neat Python API. It's portable. It can be deployed to CPUs or GPUs. And it's flexible. It's compatible with any operating systems out there. And we can visualize it easily using TensorBoard. And we can have checkpoints for managing experiments. We have auto-differentiation. And we have a large community. And there are lots of very interesting projects like neural style transfer, which try to transfer a style of a artwork onto a photograph. And we have sentence classification, and also Mozilla Deep Speech. So graphs are, in a sense, this is a very simple graph of describing an addition operation, and the nodes are the operators and the variables and all constants, and the edges are the tensors. So what this code does is it defines a graph and assign the variable a here is the output of the graph if it's evaluated, but it hasn't been evaluated. So if you try to print a, it will print out a tensor object. So how do we get the value of a? We need to create a session and run a in that session. So that's how we get the value of a. Or another way of writing will be just with tf.session as sesh and print sesh.run a. So why do we use graphs? Because it can be decomposed into subgraphs, and we can run them across multiple CPUs, GPUs in parallel. So it's more efficient this way. And also, we can save a lot of computation because only the subgraphs that evaluated to the target value will be evaluated. And we can break computation into small differential pieces to facilitate auto-differentiation. And graphs are the most common framework to visualize ML models. So this model right here is an LSTM cell. It's a long short-term memory. If you want to know more, you should attend our RNN workshop. So there are a few objects in TensorFlow that are quite confusing for those who are new to TensorFlow, mainly constants, variables, and placeholders. So constants are an object that is built into the graph itself. It's constant. It can't be. It's immutable, and so over here, if you see, if you define a, b as the constant and you add them, and you run it, and it prints the addition of this this array with this array, and this array with this array. So you get 4, 6, and 6, 8. So what's wrong with constants? Because since it's stored in the graph definition, so when constants get larger, loading graphs become very expensive. So please only use constants for primitive types, and use variables for data that requires more memory. And variables are only initialized when the session is run. I will hand over to Nikita to do a coding demo.
Okay. So first, I'll talk about the basic structure of how to create a neural net in TensorFlow. This is like a very high-level overview for specifically for supervised learning problems where you have features X and you want to predict like some label Y. But for like other types of problems, this structure might change. So the first step is to read in the data. So you can load in the data set from a CSV or wherever else you have it stored. Or you can use some of TensorFlow's interfaces to load in the data. For example, MNIST, which is a image data set of handwritten digits. TensorFlow has a nice interface for loading that in, and it provides many convenient methods. And we'll be using this data set for the demo. So after you load in your data, the next step is to define the placeholders. So placeholders act as like the input markers to a graph. So like as Aaron mentioned, a TensorFlow graph is kind of a way for, it's like a definition of how data is manipulated through the graph. But it doesn't actually contain like the actual data points in the graph itself. Like they're not hard-coded in, because then the graph would be really computationally expensive to load. So instead what you have is you have a placeholder, and you can feed in the data into that when you run your session. So the graph is created separately. It defines kind of how the data should be flowing through the graph, and you create a placeholder that marks as the input. And in the session, you actually input the data into the placeholder, and that's when it actually runs through. So for most problems, you need to define placeholders for the features X and the corresponding labels Y. The dimensions of the placeholders, so the first dimension of X and Y can be set to none. And this signals to the graph constructor that we want to have variable batch sizes. And the reason we have variable batch sizes is for training, for example, let's say you want to load in 100 images at a time and perform an optimization step. But during testing, you only want to like load in 10 images to compute the accuracy or to display what the classifications are. So you want to have variable number of data points that can go into the graph. So that's why if you set the first dimension of the placeholder to none, that signals that you can have variable batch sizes. So placeholders are not just limited to data. Basically, they're used for any sort of information that you want to pass into the graph during the session. So for example, you can use placeholders to specify a dropout probability. And dropout is like a regularization technique in neural networks, which helps prevent overfitting because it only allows a certain percentage of the nodes to be trained during each optimization step. So during training, you want some of these nodes to not be trainable to kind of prevent interdependencies. But during the testing step, you want to actually use all of their nodes. So you could use the dropout probability as a placeholder and set it to something positive during the training step and like 0 during the testing step. Okay, so after you define your placeholders, the next step is to define the variables for each layer. And variables hold the parameters of the model, like the weights and the biases. They're trainable values, and they're usually updated during the optimization step. So unlike constants, which stay static throughout like the entire execution, variables are actually updated. So when you initialize your weights, you typically want to initialize them from some sort of a random distribution, and this helps break the symmetry during the backprop step. And also the biases are typically initialized as something slightly positive. So after that, the next step is to actually construct all of the layers of the model. So like, for example, let's say you wanted to construct fully connected layers. This is the function that you would use. So X is the input, either like the input data points or the previous layer. And the shape of X will be batch sized by number of input features. So like you can imagine a matrix that's batch size long and number of input features wide. And you'll be multiplying that, matrix multiplying that by the weights, which will be of size number of input features long and number of output features wide. So when you multiply these two together, you end up with something that's batch size long and number of output features wide. So then you add the biases on, and the size of that will be 1 by number of output features. So TensorFlow will do broadcasting addition once you add that on to the result of x.w. So basically you add the bias to each individual data point. So on top of that, you add a nonlinearity activation function, and you do this for each layer. And some common examples are ReLU or sigmoid, and each of them has different properties. But if you want to construct multiple fully connected layers, you just repeat this process for how many ever layers you have. So the next step is the loss function. And this is the objective function that essentially compares how good is the output of the neural network to what you want it to be. So in like a regression problem or a classification problem, the objective function would be comparing the true values of y to the predicted values of y. And it could do this with mean squared error, which is often used for regression type of problems, or cross entropy, which could be used for classification. TensorFlow has a lot of popular loss functions already provided. But in the case that you want to do something different and like define your own loss function, it's a good idea to use the functions that they provide for basic operations like conditional if-then statements or other things like that. They have a list of operations that they have. But the reason is TensorFlow, one of the big advantages of it is it actually computes the gradients and does the backprop step really seamlessly. So if you use their functions, they know how to compute the gradients of your custom loss function then. Okay, so the next step is to define the optimizer, and there's a bunch of optimizers that TensorFlow already provided. They take in the learning rate as a parameter, and you want to set the optimizer to minimize the loss function. If you notice during your training time that the loss is failing to converge, or the loss is appearing as nan, or like something else like that, try decreasing the learning rate, because then you'll take a smaller step size and hopefully that fixes the issue. Usually it does. Okay, next is to create a session. So all of what we done before is actually like defining the graph, and now we want to run the graph. So for IPython notebooks, it's like a good idea to use the interactive session, because then you can have a session open between multiple cells and like run different things without cramming it all into one cell. But for normal Python scripts, you can use the regular session, and make sure to initialize all global variables so that like the graph is fully initialized before starting. Okay. Next is to train the model, and for each epoch, so basically for each, all of the training data, you want to go through the training data in batches, go through all of it per each epoch, and run the optimizer. And at the end of each epoch, aggregate the losses and print this value out. And this essentially allows you to see if your loss is like decreasing, so you can see if your model is actually converging. And also, especially for more complicated models, this is useful, but TensorBoard is a really great tool to actually visualize the convergence and other like cool things like that, and we'll explore this a bit more during the demo. Okay, last step is to test the model, and this really depends on the type of problem you're trying to solve. For example, if you have like classification, you could be printing an accuracy or like plotting a regression line. If it's like a network that generates data, you could be displaying that. But yeah, those are like the overall steps on how to create a neural network in TensorFlow. I guess first, are there any questions on any of this? We'll be going over a demo with like a lot more detail, but yeah. Any questions? Yeah.
Like any advantage or disadvantage to defining, I guess, your input size? Because when you specify the first dimension as an answer, you can have variable dimensions enter it. Is there an advantage to knowing your dimensions beforehand, or should you just always keep it variable?
Like dimensions as in the first dimension, or?
Yeah, the first dimension.
I would say it's like usually better to keep it as none, because then you can use the same graph for both training and testing and visualizing and like whatever else you need to do.
Okay, so it doesn't
maybe it does. I'm not sure exactly if it goes faster or not, but like it's typically like a good practice to set it to none. Like you see that quite often. Yeah. Okay, so next we'll be going over a demo. So go to this link over here, github.com/mlberkeley/intro to TensorFlow, and pull the repo that has like a few notebooks that you can use to follow along. Yeah.
Sure. I can try again.
Okay, does everyone have the notebook pulled? Any issues with that? Okay, so also does everyone have TensorFlow installed and stuff? Does anyone not? Yeah.
I lost connection.
Oh.
Is there Wi-Fi sound?
Okay. If it's a Wi-Fi issue, well, like if you can't have TensorFlow installed and like you're having issues with that, you could try going to collab.research.google.com and you can like open up a notebook there and run it online without having to. Yeah.
This might be a dumb question, but what is cross entropy in terms of loss functions?
In terms of loss functions,
Yeah.
usually it's used for like classification problems.
Yes.
Yeah, it's like a way to. It's especially good for like because like with classification problems, you're trying to see what the probability of a specific class is. So it's like especially good for those purposes.
Oh, so it's for like measuring mismatches.
Yeah, and it like specifically has to do with like the probability that comes with like sigmoid or softmax. Yeah, but you guys can go to this link if you're having troubles installing, but otherwise you can just follow along locally. So for the demo, we'll be doing a feed-forward network on MNIST, and MNIST is a data set of images with handwritten digits, and the goal is essentially to classify each of the digits as 0 to 9. We'll be creating like a 2-layer neural network with 2 hidden layers, and yeah. Okay, so first just go through and run the first few cells. Sorry, 1 second. Okay, so load in TensorFlow, load in the data sets. The first step is to create, oh yeah.
Getting a permission denied error when I'm trying to load in the data set.
Oh, what?
Permission denied error.
Okay, I'll just continue. So the first step is to create placeholders for X and Y. So with MNIST, you have 28 by 28 dimensional images. And when they're loaded in, they're flattened out into like a 784 dimensional vector. So instead of a 2D, it's like a 1D vector. So when you're creating your placeholder, first create X, which will be where the images go. tf.placeholder. And first you specify the type, which will be float32. And then you specify the shape. So because we want variable batch size, the first dimension will be none. And because each data point is 784 dimensionally long, the second dimension will be 784. Okay, and then, yeah.
It's hard to see. Can you large define?
Oh, yeah. Is that okay? Bigger? Yeah?
Yeah.
Yeah, good? Okay. Oh, bigger. Okay. Is that good?
Yeah.
Yeah. Okay. Okay, so you create X, and then the second step is create Y. So this is also a placeholder. Same of float 32. Now the dimensions, well, the first dimension is done because you want variable batch size. And the second dimension will be 10. So the way Y is given in is it's a one-hot encoded vector. So because there's 10 different digits, it's 10 dimensional, it's in 10D, and it's 0 for all of the, in most of the places, and 1 where the value is, like where the label is. So like for 3, it'll be 0 everywhere, and 1 in the 3's position. Okay, so the next step is to actually create the network. So we have, well, the network configurations are there. So the first layer, you're taking in your 784 dimensional image and converting it into 256 features. Then the second layer is keeping it at 256, and then the third layer is taking it to the 10 output features, which will eventually be trained to predict the classes. So first, the first layer of weights will be created with tf.variable. And then because you want to use some sort of normal random distribution, I'll use the truncated normal. The shape will be 784 by 256. So when you multiply in a 784 dimensional image, it'll take it out to 256. And we'll put the standard deviation as 0.1. Okay. Then next create the biases, and that will also be a variable. Now we'll just use tf.constant inside with 0.1, just something slightly positive to initialize it. And the shape will be 1 by 256 because the output of this first layer will be 256 dimensional in the second dimension. So Tensorflow will do broadcast additioning. Okay, so next is to actually create the layer. So use tf.matmul, which is matrix multiply. Don't use like the star symbol because that does element-wise multiplication. So take in the input x and multiply it with w1 and add on b1. And when you do the plus sign, that's automatically doing broadcast addition. So after you create your layer, you want to add some sort of nonlinearity on it. So here we'll use ReLU. And that's basically how you create the first layer. Any questions about this? Okay. So for the next layer, I'll just copy this over so I don't have to type it again. But what you have to do is take this 256 features and put it, translate it to, again, 256. So the weights for the second layer will have shape 256 by 256 with 0.1 standard deviation again. The biases will be of the same shape because the output is still the same shape, so you don't change this. Layer 2 will be mostly the same, except now the input will be layer 1 instead of x, multiplying it by w2 and adding on b2. So now we have two hidden layers, and now we're creating the output layer. So again, I'll just copy this over. So for the output layer, you're going from 256 to 10 because there's 10 different classes. So eventually this will be predicting which class the image is in. And the biases will also be of shape 10. For the output layer, so we'll do tf.matmul again of layer 2 and w out and add on b out. So here I didn't apply any sort of nonlinearity, and we'll get to this later. But you don't want to apply ReLU. Here's the main point, because here you're going to be applying the softmax function, which essentially will help compute what is the probability that the image is in each of the classes or each of the digits. So what's the probability it's one of the digits? Okay. Okay, I'm going to move on. So next is to compute the loss. So first we'll be using this cross entropy function that TensorFlow already provided. So here, this function not only computes the cross entropy, but it also applies softmax onto the output. So that's why in the previous output layer, I didn't add on any sort of nonlinearity, because this function will already do it, so you don't want to add that twice. Yeah. So this takes in the logits, which are basically like the output layer before softmax or anything is applied. And it takes in the labels, which is y. Yeah. So it takes in logits and y. So now basically we have the entropy computed for each of the elements in the batch, but we want one scalar number as the loss. So we have like one number to minimize. So we'll take the mean now. So loss is equal to the mean of the entropy. Wait 1 second. Wait, I'll just make this as also. Okay.
Sorry, what's labels?
Labels equals y, the placeholder we said before. Okay, so now that we have the loss, the next step is to declare the optimizer. So here we'll use the gradient descent optimizer. And it takes in the learning rate as the parameter. And I'll set it to 0.01, which is like relatively small. And you set the optimizer to minimize the loss. Okay, so the next step is computing the accuracy, and you do this by first, we have the logits as the output of the network. So first we want like the actual label that what is the class that it's predicting. So we'll say ypred, first apply softmax, because the cross entropy function applied softmax, but it doesn't actually change what the output is, so we have to apply it separately again. And then we can get what the class label is by getting the argmax of the output of the softmax. So softmax will return like a vector of probabilities, and the one with the maximum probability, the index of that will be like the label of the image that it's predicting. Okay. Similarly, we want to get the true class of y. So we'll do argmax again, but this time on the placeholder y, because that's also passed in as a 10-dimensional vector, so we want to reduce that down. Okay, so now that we have this, we can compute the accuracy. And first we'll see where the predicted value of y and the true y are equal. So we'll do tf.equal ypred class and y class. And then this will return like a bunch of booleans as an array, so you want to cast that to integers. So cast that, or actually cast it into a float. So now you have a vector of like zeros or ones, whether or not they're equal, and then you want to take the mean of that as the accuracy. Okay. Okay, so I'll skip over the TensorBoard stuff for now. I'll get to it once we actually finish creating everything else. So the next step is to like actually train the network. So first we'll set a batch size to 128 and epochs to 25. Okay, so first create an interactive session because we're using an IPython notebook. And run all the global variable initializer. Okay. So the next step is we have our batch size. So how many batches are there per the training set? So n batches. We can compute this by saying mnist.train.number of examples. And this is like an example of how TensorFlow for like popular data sets like mnist, it has like all these functions already built in, so you don't have to like take the length yourself and stuff. But divide that by the batch size, and this tells you the number of batches that we'll be running over. And just convert that to an int. And then, so now we can actually start the training process. So for I in range, the number of epochs that we have, which is 25. So 25 iterations through all of the training data. First, we'll set the total loss to equal 0. And then we'll keep summing to that. Range, oh yeah, thanks. Okay, so looping through each of the batches. First get the X batch and Y batch. And again, TensorFlow has a nice interface to easily do this. Yeah, so you can just call the next batch size with the batch size that we have, and it'll get that. And then next is to run the optimizer and the loss. So the way you do this is sess.run, optimizer, and loss. And these are both the names of variables we defined earlier. And for the placeholder, we have to actually feed in values to the placeholder. So we'll create feedDict, and that's a dictionary. And whatever placeholders you have above in the graph, you want to feed in values for those. So x is a variable we had above, and we'll feed in x batch, which is like the actual set of images. And then also y is a placeholder, and we'll feed in y batch. It's important to note here, x and y as like the keys to the dictionary are not strings, they're like actual variables. So don't make them strings. Okay. So this returns into O and L the value of the optimizer and loss. Usually the optimizer doesn't return anything useful, so we can ignore it. But with the loss, we're going to append that or add that on to the total loss. And then afterwards, we can just print the the loss for each epoch. So that will just print what the loss is. So we can run this, and that should hopefully start training. Yeah. So that'll go for a little bit, but I'll just tell you how to print the accuracy. So we're training on the entire training set, and we'll test the accuracy on all of the test set. So we can say X batch and Y batch are the next batch from the testing set. But this time, instead of taking a batch size that we defined, we'll just take all of the examples. Like that. And then the final accuracy is equal to, if we run the accuracy function that we have above for the variable. And then again, feedDict. And then we can just print out the final accuracy. So it went through 25 epochs of training, and you can see here, like, let's say you're training a model on your own. The loss starts off really high at like almost 400, and with each epoch, it's like gradually decreasing. So like for simple examples, this is like a pretty sufficient way to see if your model is actually converging and learning what it should. And at the end, it like went down quite a bit from the beginning, and then the accuracy on the test set is like pretty good also. So yeah, like that's basically how you create a model. Are there any questions? Okay. We'll stop like for a quick like 2 to 3 minute break, and then afterwards we'll go over how to actually visualize this in TensorFlow. So yeah, you can ask any questions if you want to.
I'll just have a personal question. I guess I'll just have to install it. I guess it's not this. Oh, okay. Yeah. So we can
Sorry, can we,
Oh, sorry, yeah.
we could like zoom in on the first blocks. The big one at the top. Are you using
Which one?
Oh, yeah, so like it's kind of like I know for sure I downloaded TensorFlow, like installed it directly.
Yeah.
Oh, I missed it. Oh, yeah, I forgot.
No.
Should I move down to the next one?
Oh, sorry, 1 second. Okay, yeah, next one.
Oh, my finger's not working.
Should I keep going now?
Yeah. Yeah. When you're ready.
Okay, so I'm gonna keep going in the interest of time, so we have time to get to the lab also. Okay, so now like we created the model and it like trained pretty well right now, but now we'll go over how to visualize it in TensorBoard and like what kind of statistics you can see about it. So like I'll start from the very basics. So first, what you can do is just to create TensorBoard is create a writer that like keeps track of the logs. So you do that with tf.summary.filewriter, and then pass in the place where you want the logs to be written to, and then set the graph to equal the default graph. So in TensorFlow, you can actually have multiple different graphs, so you want the default graph here. So put in that line right there, right after you initialize your session. And then I'm gonna start by running this for now. So,
Could you scroll that cell a little bit to the right?
this way? Yeah.
What's the difference between a regular session and an interactive session?
So if you create a regular session, you have to use with tf.session as such as like a heading. And then basically with IPython notebooks, interactive sessions allow the session to continuously be open. So it's like as if you had it open in terminal, like the difference between running a Python script versus like having Python open in the terminal.
So if you use a regular session, session closes after the block.
Yeah.
finishes.
Like here we were able to train it and then in a new block print out the test accuracy all with one session. So in a regular session you wouldn't be able to do that.
So like in regular code, you would just use a regular session.
Yeah. Okay. So the way you open up TensorBoard now is go to your terminal. Let me make this bigger also. Okay, can you see that? Okay. So the command is tensorboard --logdir equals the path that you specified. So for me it's log/train. Okay, so when you do that, it'll give you a link. So usually it's at the port 6006. So I'll just, I guess I have it over here. Sorry, 1 second. I guess zooming doesn't work too well on this, but right now all we did was we created the TensorBoard log and we just displayed it. So we didn't like format at all. So even though we have variables and everything, and for us it looks pretty neat, for the actual graph, each of the nodes don't actually have names. So like the weights and the biases, they don't have names in the graph's point of view. So when you actually print out the graph here, and this graph is good to see like which node feeds it. Yeah.
I'm sorry, could you show me the TensorBoard command from the terminal one more time?
Yeah, it's here, that one. So basically the graph doesn't know what the names are, so that's why when you look at it, it looked really messy, right? Because each individual variable or anything we created was put as a separate node. So like first what we can do is go ahead and like clean this up a little bit so it's like actually easier to visualize and like understand what's going on. So the way you do that is with name scopes. So right now, like I said before, x and y are variables for us, but for the graph, they don't actually have a name. So the way you can do that is with tf.namescope, and then here it'll be input, and then just tab this over. So for the placeholders, we'll call them input. For the entire network, we'll call it network. And then tab all this over. So this is when you tab it over, it's like saying everything underneath here has the name network. And then here we'll call it and then I'll rerun it so we can visualize it. And with TensorBoard, basically, like, I'll just show you here. So in the logs folder that I created, there's train, and then there's one log because we ran it once. If I ran it again, it wouldn't override this log, it would create another log over there. So when you actually open up TensorBoard, it gets really messy with like different runs and stuff. So it's usually like pretty nice if you can change your folder name over here. So it like creates another folder and like you can always make sure there's only one log being run at a time. So I'll run this. And then when you go here, I'll just rerun it with the new name of the folder. Okay, and it's at the same location again. Okay, so now you can see the graph looks like a lot better than what it did before, right? So this is the input, this is the network, cross entropy loss, all the gradients are stored there. And you can see like the input feeds into the network feeds into the cross entropy loss, but also the input, which is like specifically the Y placeholders, feed into the loss. So you can like visualize it over here and see like, is my graph connected up the way I want it to, or is like something that's not supposed to be connected, like actually connected. So, and also if you want to see like what's actually inside the network, you can click on the plus button. Yeah, you can click on the plus button, and it looks a little weird because it's in zoomed in view, but like you can see like the original graph over there, so you don't like lose that. Okay, so I'll just stop this for now. But okay, so we have the graph down, but also you can visualize a lot of other things in TensorBoard. So you can visualize the accuracy, you can visualize the loss like as functions and plots. Also, you can visualize how the weights are changing over time. So like, are they actually training or are they staying constant? So we'll create all those summaries right now. And the way you do that, so first for accuracy, for example, so it's tf.summary.scalar, and then you give it the name that you want it to appear as, and then the variable name. So we'll do loss and then accuracy also. And then also you can visualize the weights. So I'll do a summary, but I'll do a summary histogram for the weights of each layer and for the biases. So then I'll just copy this over for all of the layers. Okay, so now you have a bunch of summary variables for each of these different quantities. To actually run these summaries and visualize them, you have to run them. So instead of running each individual one, you can create a summary op that merges together all of the different summaries into one operation that you can run. With that command, tf.summary.mergeAll. So once you do this, now you have one operation that has all your summaries, and then in the training period, instead of just running the optimizer and the loss, you also want to run the summary op. So we'll call it summary and then run the summary op in the list, like that. And now with that summary, you want to write it to the file writer. So writer.add summary, the summary that was run. And then this next input will be like the x-axis, essentially, like when did it happen. So you can say epoch number, so the current epoch, what are we on, times the number of batches that we'll go through, plus the current batch that you're on. So this allows like it to be continuously increasing instead of like going up and down as the batches change in each epoch. So once you do this, and then I'll create another folder again. Oh wait, 1 second. I have to run this cell. Okay. So I'll just show you how this is visualized also. So this is where it gets pretty cool. Hopefully it works. Cool, okay. I'm gonna zoom out a bit here. Hopefully you can see it still, yeah. So like in the scalars tab, now before we only had the graphs tab, now we have all these other tabs. So in the scalars tab, you have the accuracy and the loss as two different plots. And when you scroll over it, you can see the time step and you can see the value. So here it's like 30%, 40%, and then like right now it's around like 90%-ish. And this is being updated real time. So let's say you had a model that was training for like 5 days or something. Every day, instead of like just having this printout and like going and checking the numbers and like hoping it's converging, like you can actually just have this plotted out and like printed in real time so you can see like how is my model doing over the course of like a long period of time. Like did it like consistently increase or like did it dip and then go up again? Like all that information is stored for you. Also in the histograms tab, because we plotted histograms of all the weights, let's say in this tab your accuracy wasn't increasing or your loss wasn't decreasing and you're like wondering what's going on. You can go to the histograms tab and see is the model actually learning something. So ideally we like set the weights to and the biases to be something initially and then we're running the optimizer to train it, right? So you want to see if that actually is working. So for example here, like with the biases especially, more than the weights, like you can see it very clearly here. It started off in that distribution. So the x-axis is like the values of the that's in the vector, and then the y-axis that's highlighted right now. Like this y-axis is the frequency, and then the depth dimension is like over time as it's training. So it starts off like this, and then it like peaks up a lot more. So like you can clearly see that like the model is changing, it's updating its weights, and it is learning. So yeah, like that's like a good way to like diagnose what's going on. And like let's say for example we didn't do this correctly and like we made a mistake. So let's say that instead of in the cross entropy loss, we instead of putting in the labels, we put in the predicted value of y, like that. Right. So now like the logits is like before the softmax function and ypred is after the softmax function, but essentially they're like mostly the same thing. They're not like the true labels or anything. So we can see what happens if we do this now. And then okay, so here you can see that the accuracy is not actually increasing. It's like staying mostly constant, and specifically it's like more or less around 10%. And there's 10 different classes, right? So 10% accuracy means it's like basically randomly guessing, and it's not really learning anything. Moreover, you can see that when you open up the histograms, I guess this still has the runs from the last time. Actually, yeah, some of these are last time's ones, but with the biases, you can see it clearly. They started off as all 0.1, which is like a constant, so that's why it's flat. And as time is going on, it's not changing. It's like continuing to stay flat. So you can see that it's like not training at all. So like then you can go back and see like if my model is not training, what's going on, and like especially if you go to the graph section, I think it should show it here. Yeah, like you can see here that, or actually wait, I guess now it's a little bit complicated, but if you like make your namescopes a bit clearer, you can see that the inputs wouldn't be feeding into the cross entropy loss because y isn't going in, it's only ypred. So like that's a way you can use TensorBoard to debug, and like for this example, like it's a pretty basic neural network, so it seems like a little basic, but and you don't really need to do this, but for much more complicated ones, this is really useful for seeing like exactly where is the issue. So yeah. Any questions on this example overall? No? All good? Okay. Okay. So next, like just so you can get an idea on like how to create a neural network and like try it out for yourself, we have a lab. This shouldn't take too long, but I think it's a pretty cool application of fully connected layers. So in the lab, you'll be building an autoencoder, and what an autoencoder is it takes in an image, and it's basically an identity function as a neural net. So it takes in like some sort of data, and it's trying to reconstruct that data, except it has a bottleneck in the middle, and that bottleneck tries to force the network to learn something efficient and useful about the data. So instead of keeping, like, for example, with the MNIST images, instead of having 784 features, you want to learn it in only 128 features. So you're trying to learn a more compressed version of the image. So ideally, and it has like an encoder and decoder portion. So like you feed in the original image as the encoder into the encoder. It creates like a small latent space. And ideally, with that latent space, it should be able to reconstruct the image in the decoder step. So that's a normal autoencoder. Here we'll be doing something a little extra. So this is a denoising autoencoder. So I have a function that takes in an image and it like gets rid of half of the pixels or a certain percentage of the pixels. So that's why you can see that this 2 is like a lot more blurry than this 2 and it's like a lot less clear. So the goal that you have is how do you reconstruct the original image given this blurry image? So let's say for the training data you have both the blurry images and the real images. And in the testing data you only have the blurry images. How would you reconstruct the originals? And like how well could you do? So like these are the network parameters that you have. You're like first taking it from 784 all the way down to 128 to learn something efficient, and then like reconstructing it back up to 784. So yeah, like that's like an overview of the lab. If you have this repo pulled, here you have the student version of the denoising autoencoder. So again, this picture is here that says the network parameters, and this is the function that has the masking noise. It gets rid of like a certain percentage of the pixels. Here are the network parameters, so you don't actually have to like come up with what numbers to use. And what your task is kind of to fill in the dots. So mostly fill in the shapes here and like get comfortable with what shapes should be put in as the input and output to like make this work. And also like another part that's like a little tricky and different than the MNIST example of classification is the loss function, right? Because now you don't have a y value that you're trying to fit to. So like what are you supposed to make the like what are you comparing the output of the network with? Like what do you want it to be? That's what the loss should try to help you achieve. And yeah, and then just fill out like the training process, and we'll give like maybe around like 25 to 30 minutes to work on this. Like please work with neighbors. I'll like check in every like 10 minutes or so. Yeah.
Before you showed 2 graphs, one was logarithmic, one was exponential.
Yeah.
It was like loss and
Accuracy.
Are those just inverses of each other, or do they really have
So, like,
different independent variables?
The losses, so they're not independent variables. They're like very dependent.
They seem like really the same curve.
But they're not like exactly inverses. So the loss is like the average loss over all of the examples, and then the accuracy is like the actual percentage accuracy on the test data set. So like they seem.
I'm a physics major, by the way.
Yeah.
I'm doing this because LBL uses Tensorflow for like my research project.
Yeah, but like they are inverses in like shape, but like there'll be like a proportionality constant that's off between both of them. But like you can't really see it there. But yeah.
And then for stuff like you guys add a nonlinearity function. Is that like just basically so you can stir the pot? Like how you're saying you want to use a random distribution of your biases or your weights first, so that like your AI or your neural net like kind of like figures a way out. It doesn't just take a super obvious guess every single time.
So like the random distribution we started off with was like the initialization. So like you want the weights to be initialized randomly so that
It has to fix them.
yeah, it has to fix it, and you don't want it to have like some symmetry there because then like it could get stuck in like some sort of optimum that's not like the true global optimum when it's decreasing.
Oh yeah.
And then like the nonlinearities are like let's say you had like a bunch of layers in your neural network without nonlinearities. At the end, it could only like yeah. So like basically like it's like a matrix multiply on the input, right? And then that's like the composable function. So it'll just be a bunch of matrix multiplies, but at the end that's still a linear function, right?
Yeah.
So like the nonlinearity helps you like learn nonlinear functions, so like curves and like other sorts of nonlinear things.
Okay. My final question was, at one point you said don't use the star because that's
Element wise.
the element multiplication. Then you said you had a plus B.
Yeah.
You used a different term. You said it's something.
That's like so basically the bias term was like 1 by the number of alpha features, whereas you have batch size as the number of like for x you have batch size as the negative. So this one will go and do broadcasting.
Broadcasting. So can you explain? So I've taken Python.
Yeah.
So what's broadcasting?
So it's like even though the first dimension, so like ideally if you're like adding two vectors, you want the shapes to be
Oh, sure.
Yeah.
So here, like let's say it's like 784 by 256. Right, you can add that with 1 by 256. Even though it's like the dimensions are separate, as long as the second dimension is the same, it'll take the first dimension and like place it on each of them.
Oh, so it kind of fits it.
Yeah.
Okay, cool. Thank you.
Yeah.
Thank you for knowing your stuff. That's really solid.
Also one more thing, for anyone who's leaving, it would be really great if you could fill out the workshop feedback form, especially because next workshop will be like PyTorch, so it's also a neural net library, so we would really appreciate like what went well or what didn't go well so we can fix it.
Must have like some sort of
Okay, I'm gonna go over like the first part of it, like creating the encoder and decoder. Yeah. So here are your network parameters. Okay. So for creating the placeholders again, your shape is first dimension is none, second dimension is the number for the input, which is 784. And same for X noise, because even after we're adding the noise, the dimensions of the image isn't changing. So yeah, that's why it's the same dimension there. And yeah, like this is like another way to add names for TensorBoard, like adding the name directly here instead of using namescope. But for anyone who didn't get this part yet, you can copy it down. Anyone need this, or can I move on?
Are you gonna be posting this online?
Yeah, I'll post it. Yeah. Okay. So yeah, the next part is like actually creating the weights or defining the shapes of the weights for encoder and decoder. So first, you're going from the number in the input to the number in the hidden layer, and then in the second layer, you're going from n hidden 1 to n hidden 2. So the n hidden 2 is like the smallest 128. And then for the decoder weights, you're going from hidden 2 out to hidden 1 again, and then from hidden 1 back to input. So that's why, like, if you look at this, it's like you can think about it like the first dimension is like what's the shape of the input, and the second dimension is what do you want the output shape to be. And then again, do that for like the next layer and the next layer. So that's like how you get the weights, the shapes for the weights. Any questions?
Sure, I don't know if this is.
Okay. For the biases, basically, yeah, you want the shapes to be what the shape of the output of that layer would be. So for the first layer, the output shape is n hidden 1. So you want to add on something that's also of dimension n hidden 1. Similarly, for the second layer, n hidden 2, and then back out to 1, and then back to n input, which is the reconstructed image. I'm going to scroll up a little. Okay, so next is like actually defining the encoders and decoders. So first, define matrix multiply together x and the weights of the encoder for layer 1. Add on the bias weights, and then apply sigmoid to all of that. So as your nonlinearity, it'll be sigmoid this time. And then for layer 2, do the same thing, except for now the input is layer 1. Your weights are of the weights of the second layer, and then the bias of the second layer also. Yeah. And then for the decoder, it's pretty similar, except now you're using the decoder weights 1 and bias 1, and then weights 2 and bias 2. And again, the input for the second layer is the output of the first layer. And like the way we defined it up here, we just created a dictionary with the keys being like each of the layers, so you don't have to like, you can just have all that stored in one spot instead of having to like keep track of that information while actually using the functions. So like the input to the encoder would be like the overall image, and then the input to the decoder would be like the 128 dimensional agent space vector. Okay, so keep going. Or actually, how far did you guys get? Like who finished like the entire training step? You finished training?
Yeah.
Cool. Did you see the output?
Yeah.
Okay, cool. Who like finished, I guess, like the optimizer section, like this area until here? Yeah? Okay. Okay, yeah, so I'll just go through all of it then. Does anyone want like more time to work on all of it, or should I just go through it all?
Just go through.
Yeah, okay. Okay, so creating this, so next the encoder operation is just encoder of X noise. Make sure to feed in the noisy version of X here, not the original, because you want like the input to be the noisy input so you can like make it not noisy. And then the decoder will take in the output of the encoder, which is the 128 dimensional vector. And then your predicted value is basically the decoder. It'll be like a 784 dimensional vector of what's supposed to be the non-blurry image. Yeah. Okay, so for entropy, we'll be using the log loss over here. And you're comparing the predicted value, which is the output of the decoder, to the original image X. So this is not the noisy image, it's the original image. And this is how you allow the autoencoder to like learn how to clean up the image that's noisy coming in. Because if you made this X noise, or if you made the input over here X, then it would just be learning an identity map. But making this X noise and making this X allows it to learn how to like fix the image. Okay, and then again, when you're reducing the mean of the entropy for the loss, the actual loss term. And then here, we'll use the RMS prop optimizer, and we'll set the learning rate equal to the learning rate defined above. Set it to minimize the loss. This is pretty similar to what the gradient descent optimizer, how we used it in the last example. Yeah.
Make it a little bigger.
Oh yeah, sorry. The only issue is if I make it bigger, I don't know if you can see the entire line. Let me know if you want me to like scroll left or right. Okay, so next just like import the data that's given and then start an interactive session and initialize all the variables. Make sure to not forget to run that ever. For each training epoch, you want to go through the batches and apply the noise function first. So the noise, feed in like 0.5, for example, to get rid of half of the pixels. And then run the optimizer and the loss. Here the feed dict, you're feeding in the original value of X and the noisy value of X. So there's no Y. Instead of Y, like the true Y is kind of the original X. Yeah, and then the input is the noisy X. And then, yeah, add it to the loss and then print that out. So I ran mine, yeah, for like 10 epochs, and like the loss went from 100 down to 24, which is like pretty good. And then the cool part about this is like the actual results. And it's pretty cool how just like a feed-forward network can like actually denoise the images. But like if you use the plotting code afterwards, in like this is the second row is the noisy image, this is the original, and this is what it reconstructed. So it's like pretty cool how similar this is to the original, right? Like even though the noisy image is like actually quite bad. And then if you look at the grayscale version of it, like you can see how faint this is, but then like it reconstructed pretty well because it was given this as the input. And all these images were ones that it hasn't seen before. So this isn't the test set. It didn't memorize this for like some of the training examples or any. Like they're similar, but they're actually different images. So yeah. Any questions on like any of this? I think this is like a pretty cool application of like feed-forward nets. Okay, cool. Like any questions overall? Like if you want, like we can stay afterwards also. But yeah. Okay, I guess if nothing else, then like please make sure to fill out the feedback form. We'd really love feedback for the next workshop. Next week, we'll be having an intro to PyTorch workshop, so you can see like what there's like quite a bit different than TensorFlow, but like a lot of people really enjoy it. So like you can come try that out also. And throughout the semester, we'll be having workshops on like other deep learning topics, and the schedule is posted on Facebook. So please try to attend those also. Yeah, thank you. Yeah, we'll post that video or like the screen recording. Something we'll post it to YouTube. Yeah, to the ML Berkeley channel.
This time